More about functions. Here we go with next to the last topic in Chapter 3. We will be graphing special functions, very special. And we'll be looking at the composite of two functions. So I'm trying to think, have we done a little? I think we actually have done a little tiny bit with this already, so we're going to get a little more formal about it today. When I was a kid, I got a B in science and an A in math too. Dad seems to remember those temptations. It's a little different today, isn't it, with electronic delivery. Evaluate the function y equals 3x minus 4. Now, what type of function is this? That's right, it's a linear function. We know that because the powers that we're dealing with here are all first power. So instead of writing in x as an unknown, we're going to write in a known value of x, 7. And we'll find out what y is when x is 7. So that's going to be 21 minus 4. So y must be 17. If function f, remember this is the same as y, f of x is just a functional notation, and it means the same thing as saying y. If f of x equals 12 divided by x, what is function f at 3? So we're using the same idea. Every place we have an x, we're going to substitute in the 3. So we're saying the value of function f at 3, and there's the 3, what will it be? Function f at 3 equals 4. Simplify this expression. The absolute value of negative 3 is a positive 3. And then we're going to subtract the absolute value of negative 3, which is again a positive 3. Given that y is a linear function of x, and that y equals 4 when x equals 2, so we have 1 point, don't we? When x equals 2, y equals 4, and y equals 8, and we also have another point. When x is 3, y is 8. Find y when x equals 5. So let's figure out what our function is first. What do? We always start by figuring out what the slope is. At least, I think that's a smart way to go about it. Remember, slope is rise over run, or the change in the vertical over the change in the horizontal. The change in the vertical is noted here in our y's. Let's start with this one. We'll say 8 minus 4. And then we'll make the same comparison here. We'll start with this point. 3 minus 2. That'll give us the change in y divided by the change in x. Change in x is 1, so I can ignore that denominator. The change in y is 4. Our slope is 4. We don't know what our y-intercept is yet, but we can figure it out in just a moment. We're going to use the slope-intercept form of a linear equation, which is y equals mx. So this would be the m in this case. In our example here, our m is 4, so we're going to say 4x, and we don't know what our y-intercept is. So we'll put that in as b. We can use either one of these points. Which one do you think would be easier to work with? I agree. Let's use the one with the smaller values. So instead of putting in y, we put in a known good value for y, which is 4. And then we've got 4 times 2. So our b has to be equal to 4 minus 8. Agreed, this is 8, and we subtract it from both sides. B equals a negative 4. So now we have our equation. Y equals, m is 4. So 4x plus b, and our b is a negative 4. So what is y when x is 5? We're all set to find that out right now. Y will be 16. Step function. This is also referred to as the greatest integer function. Actually happens a lot around us. Does the step 2.8 equal 2? Now notice these brackets. That's the greatest integer function. We know if we had f of x equals, that we're talking about absolute value. So these different symbols tell us different operations are going on. In this case, it's the greatest integer. So let's figure it out by looking at our little graph. I haven't put a scale on this. If no scale is there, we would generally assume that each grid is 1 by 1. Does 2.8 equal 2? Greatest integer of 2.8. So let's find 2.8 here. Here's 1, 2. 2.8 would take us right. Whoop! I better mark it with a different color. So 2.8, this one here, we're going to mark it right here. 2.8. We said it would be right about here, right? Probably doesn't show up very good. Let me hit that a few more times, make it a little more evident. And then does that equal 2? Well, here's 2. And are they at the same point as far as y is concerned? Yes. How about negative 2.8? We'll find that now. Let's see. Negative 1, negative 2, negative 2.8, which takes me right to here. I'll mark it. Does that equal the greatest function, the greatest integer function, negative 2? Ooh, no it doesn't, does it? Now the reason for that, this kind of helps us understand what the greatest integer function is. Let's start with 0. 0 is an integer, and in the greatest integer function, the output of this function stays at 0 until it reaches 1. Then it jumps. So it's a discontinuous function. It jumps up to 2, and it stays, it jumps up to 1, and it stays there until it approaches 2. When it gets to 2, it jumps up again, and then it stays equal to 2 until the input is 3. That's why it's called the greatest integer function. It gives you just the integer until you get to the next integer. So we could graph this function, couldn't we? Let's put together a little t-chart to help us out with this. This will help us understand the greatest integer function, x and y. And what do we usually do? We say, okay, we'll try 0. In this case, I think, because we're dealing with the greatest integer function, we might want to try some fractional values. I don't usually, but here it might be a good idea. And then we'll do negative 1/2. Oh, come on. Negative 1/2 and negative 1. Let's put a negative 1 in. Then I would have y equals negative 1 minus the greatest integer for negative 1. Well, what is the greatest integer for negative 1? Here's negative 1. And the output of that is negative 1. Okay, so this will simplify to negative 1 minus a negative 1. So that's the same as, we better extend this page, negative 1 plus 1. So y equals 0 in this case. What happens when I've got y equals negative 1/2? And now I'm going to subtract the greatest integer for negative 1/2. Let's see what that is. At negative 1/2, what is my output? It's negative 1. So this is equal to negative 1/2 minus a negative 1. That will simplify. It'll equal 1/2. Positive 1/2. What about when I get to 0? What is that going to be equal to? I'm going to erase some of this. We'll just clean our slate here so we can move forward. When x equals 0, y will equal 0 minus the greatest integer associated with 0. And at 0, the output is 0. So 0 minus 0, we're at 0. How about the next one? Y equals 1/2 minus the greatest integer for 1/2. Up we go. See what that is for 1/2. When x equals 1/2, y equals 0, doesn't it? Okay. Y equals 1/2 minus 0. So that would be 1/2. Now we'll do y equals 1 minus the greatest integer for 1. Happen to know at this point that that is going to be a positive 1, so y will equal 0. Well, let's plot those points. When x is negative 1, y is 0, so we've got a point right here. When x is negative 1/2, and you notice what my scale is here, so this is 1/2. Negative 1/2, y is 1/2. When x is 0, y is 0. When x is 1/2, y is 1/2. When x is 1, y is 0. Now there's something funny going on here, and it's a little bit hard to figure out with the points that we've got. Maybe we should try plotting still some additional points to see if we can figure out what is really going on here. How about if we plot 1/4 and see what happens right between here and here? That might give us a clue as to what's happening. Okay, I meant to say x is 1/4. At x is 1/4, we're right here. What is y? 0. Okay, so when x is 1/4 and we subtract the greatest integer associated with 1/4, 1/4 minus 0. Is that right? Yes. So y is 1/4. It's right here. Well, I think what we're seeing, and you could try this on your calculator, find that greatest integer function. We're seeing this interesting looking graph. At least I think it's interesting. How about graphing this one with this step function? I'm going to wipe off our previous t-chart and all right. When we try the same approach, I suppose, 0, I'm going to say 1/4, 1/2, and 1, and negative 1/2 and negative 1 for my x values, and we'll see what happens. Well, yikes. There's no way I can have this greatest integer function be equal to 0, and anything, I can't put anything in that will make this 0. So I can't put in 0. I have to say that x cannot be equal to 0. What else do I have to say? It must be it has to be either greater than or equal to 1 and less than 0, right? There is that gap, and let's show it right here. There's a gap here where we won't have any value. We can't have anything at 0 and up to 1. We can allow 1, but we cannot allow 0. So that tells me I can't use this. I can't use this. I can't use this. So maybe I'll go to 1 and 1/2 to get a few more points in here. When y, let's see, what will y be when x is equal to negative 1? We'll have negative 1 in the numerator, and when x is negative 1, y is also negative 1 for a step function, right? So y would be 1. If this were negative 1/2, I'd be saying what is the step function when x is negative 1/2, and we can see that it would be still negative 1, so that would be positive 1/2. When Let me erase that. When x is 1, we'll have 1 over, what's the step function at 1? It's 1. When x is, I'm going to erase again. When x is 1.5, I'll have y equals 1.5 divided by, what is the step function at 1.5? It's 1. Seems to me I'm going to need a few more values here. Let's slip something in here. I've got some space I can create, so I couldn't use those. How about we try 2 and 1/4. All right. So we'll try 2. Y will then equal 2 divided by the greatest integer at 2, which is 2. So y would be 1 here. What about 2 and 1/4? Well, at 2 and 1/4, it's still 2. But this will divide out a little differently, won't it? Let's see, we have 2 and 1/4 is the same as 9 over 4, isn't it? And instead of dividing by 2, we're going to multiply by 1/2. And we'll have 9 over 8. So this is 9 over 8. And what happens if we go to 2 and 1/2? Am I getting carried away with this thing? You're probably so bored. Let's see. Now I've got y equals 2.5 is the same as 5 over 2. I might as well start with a fraction. And at 1, 2.5, my y value is 2. So I am going to stay with the 5 over 2, change to multiplication, and flip this from 2 to 1/2. And I've got 5 over 4. Now let's plot these points and see what we have. I actually like these where you can't quite predict what you're going to get. It's a little mystery, which we don't have that often. Okay, negative x and a positive 1. So I've got 1 point right here. And then negative 1/2 and a positive 1/2. So I've got a point right here. And now I know that I don't have anything for a bit. Then at x equals 1, yeah, we've done that and that. We'll go down here. We have 1 and 1, so it would be right here. And then at 1.5, which would be right here, y is also 1.5. All right. At 2 1/4, which would be right here, y is 1 1/8. 1 and 1/8. This would be a quarter, so I'd be right here. Oh, come on. I hate it when it does that. At 2 1/2, we're at 1 1/4, which would be right here. Well, something strange is going on. Let's get the calculator out. So let's clean this up a little bit, because I just noticed I never wrote our answer over here. This was a no. And also, although I plotted this one, I never plotted this one. At 2, y is 1. So it seems pretty clear that we've got something sloping Oh, sloping. It seems to be sloping differently. Did I plot wrong? See if we could do this with our calculator. Now, just to prove to ourselves that we actually are headed in the right direction here with our function, notice I go to the math key, and now I'm going to go over to numbers, and there's something here that I think is the greatest integer. Let's test it. One of the ways I'll test it is to try putting in some values that we have had and see if we get what we know are the right answers. So if I put in 2.8, what will be the greatest integer in the case of 2.8? 2. And if I put in math over to number and then down to integer, we'll do negative 2.8. What is the answer going to be for that? It's going to be negative 3, right? So it looks like we were in the right place here. So let's try graphing that. We'll say y equals integer of x. Let's see what that graph looks like. Oh, something more we should think about, which we haven't had to talk about yet. We're looking at a discontinuous graph, and all of a sudden something comes up that hasn't been important before on the calculator. There are two modes. Let's go down here to connected. There are two modes in your calculator. One is connected, where it will draw a line between all the points. We don't want that to happen here, do we? So we're going to go to dot mode. We'll enter dot mode, and now we'll graph it. Ah, now it's clean. Okay, let's try graphing this one, because even though we've spent a lot of time putting some points up here, it's not entirely clear what this is supposed to look like. So we'll go back here and we'll say, let's clear this. We're going to say x, there's my x, divided by, and now we want the greatest integer, so I go to math, over to number, and down to integer, and that's going to be x. I'm putting a variable in there. Close it, and let's see how that graphs. Really? No wonder it was confusing. Let me put it, we're going to adjust the window. So we're going to say our window is from -2 to 2 with a scale of, let's make it 0.5, 1/2. Actually, yeah, that'll match what we've got there. And then for our y, we'll say the lowest value will be, well, let's make it look exactly like this, -2.5. I'm going to go back up here and adjust that. -2.5, 2.5. We'll make it look exactly like the window that we drew, 2.5, with a y scale of 0.5. Let's graph that. Well, that is a terrible looking graph. No wonder we couldn't figure it out. Oh my goodness. Look at this thing. And let me make sure that I'm in the right mode. I am. I'm in dot mode. Crazy looking thing. Oh, wow. You know, I never graphed this one before. I always skipped over it. It is so much fun. It's going, let's see, here's 1, 1.5, 1, 1.5, 2, and then it drops down, 1, 1.5, 2, and it drops down, and then it goes up at a less steep angle. How interesting. And this, the one thing we had figured out though, hadn't we? That we were not going to see anything between 0, here's 0.5, and 1. Oh, hey, while we're at it, why don't we go ahead and plot this function here, because this one might be a little better. So we're going to say this is y is equal to x minus the greatest integer. So we go math over to number. You better be doing this with me. If you don't have your calculators out at home, I'm a little upset with you. X. Okay. Now let's see what that looks like. You know, I don't like my calculator because it's supposed to be in dot mode and it just connected them. I know it did. So I'll graph connected, and now I'm going to go back. I've noticed this about the TI before, that you put it into dot mode and for some reason it doesn't stick. Alright, there, finally it looks right. This one over here, I bet you anything there's nothing right there. And I'm so curious about it. I'm sorry, kids. I just have to try it. I know, obsessive compulsive. Alright, x divided by, and we're going to find greatest integer. Go over to number, down to integer, and we put in our x again and close the parentheses, and we graph it. And it looks like there's something coming down here. I didn't trust that at the time, but I had forgotten about how peculiar this calculator can be. So I'm going to put it back into connected mode, and now go in again. I'm sure this can't be the best way to do it, but and put it back into dot mode and graph it. There. Oh, yes. Oh, yes, yes, yes. That looks like you would expect. All right. Oh, my goodness. I don't know. I find it a little bit exciting. You probably don't. I'm going to try and knock out what I had put in wrongly. So what I actually have is something like this, and something comes down to, but doesn't actually include 0, and then over here it's at about half the slope. I guess that's exactly what's happening. It keeps going up and gets shallower and shallower. Great, great function, just for the fun of it. I will try to get through this quickly now. The step function, absolute value function can be seen as a step function. You know that any time we've had absolute value, we've had to separate it out. If we wanted to get rid of absolute value brackets, we had to separate it out into two parts. One which was the positive part, and the other which was the negative part. And we always made negative everything that was between the brackets. That's basically a step function. And when we graph it, we're saying we're going to graph this function, f of x equals x, for all positive values of x, and we're going to do this one for all negative values of x. And what we end up with is, here's our positive, which includes 0, and here's our negative, which doesn't include 0. You notice this one we included 0 and this one we didn't. That is entirely arbitrary. We get to choose which one we associate the 0 with. It doesn't matter. The thing that does matter is that it gets included, and that it only gets included once. The composition of two functions. If I say that function f is the squaring of x, and function g is adding 2 to x, what will it mean if I say that my input to function f is going to be function g? Here my input was x, and I squared it, so if I put in function g, what am I going to do? I'm going to square function g, and function g is x plus 2. Okay. All right, let's try some of these. If function f is multiplying x 3 times and function g is adding 2, then function f of g to the 4th will be function f of, what is g? X plus 2. Oh, wait a second, back up. It's function f right here is 3 times whatever our input is, and our input in this case is x plus 2, only the x is no longer x, it's 4. 4 plus 2. So what is the value of function f of g at 4? This is nested, isn't it? It's 3 times 6, or 18. All right, let's reverse it and say we're going to start with function g. Function g, and instead of putting in x, we're going to put in function f. And we're going to put in function f at the value of 4. So what is function g? Let's look at it. X, so there's our input, plus 2. And what is the input? It's function f, which is x squared, and our x is 4, so it's 4 squared. What's the value here? 60. Oh, that's interesting. Turned out in this case to be exactly the same. 18. All right. Let's try another couple. Now we're going to say function f is doubling x, and function g adds 5 to x. So this is going to equal, let's see, function f is 2 times whatever the input is. The input is g at 4. G will be 4 plus 5. Wow, these are carefully designed, right, to always give us 18 as the answer. I'm not sure that was wise on my part. All right, how about this one? Function g, we know g takes x and adds 5. Well, it takes the input and adds 5. And our input in this case is going to be function f, which is 2x, but our x is 4, so it's 2 times 4. So what's this going to be? Oh, finally, I'm actually demonstrating they don't always equal 18. 8 plus 5, 13. No, they don't always equal 18, and they don't always equal each other. When you do the reverse, it doesn't always come out the same, so thank goodness I put that one in there. Done. Yes, I am sure you might have some questions here. Bring them to class. Questions welcomed.